Okay, thanks for dropping in, guys. This is going to be a crash course on systems engineering run by myself, the Finch systems lead. That's me. I'm currently the outgoing optics lead. Fairly new to the role. I started as the systems lead about a month now. I am studying engineering science aerospace, of course, here. I'm MSci 2T3 plus PUI. I'm currently PUIing at MDA for software engineering. And a fun fact about me, I've destroyed many cameras. I'll give you a few examples of a couple. When I was little, I lost my GoPro to the ocean because I didn't have a strap for it. And a wave pushed me over and I let go of the GoPro and it disappeared. One other time, I was filming running water in slow motion and I dropped the camera into the sink. That one's done. I had a smartphone that supposedly was waterproof. Of course, then when I tried to film action shots underwater in my pool, it died. It was not waterproof, unfortunately. So lesson learned is don't trust me with your cameras. I'm surprised perhaps you're trusting me with yours. Okay, so here's the agenda for today. Let me put up on my screen. Okay, so a couple of bullet points we'll hit. I'll introduce the concept of systems engineering as a whole. We'll talk a little bit about the engineering design process. That conversation will look very similar to the conversations you might have had or might be having in your engineering design courses. Except they'll be adapted to what we do internally here at UTAD. The systems engineering engine, I'll present that mechanism. That is our systems engineering workflow that we adopt on the team. I'll take a look at project management. I'll give you an overview of our productivity ecosystem. So that is effectively the network of all the tools and platforms that we use on the team that you'll start to get familiar with, of course, for your time on the team. We'll take a look at engineering requirements, the importance of those. And at the very end, I'll give you guys a fun design challenge if you stick around. Okay. So what is systems engineering? NASA defines it as a methodological, multidisciplinary approach for the design, realization, technical management, and operations of a system. The outcome of such a system, as in an engineered system, is effectively a combination of components or subsystems that come together to perform a useful function. So in this case, our satellite is a system. Finch is itself a system. And specifically, the role of systems on the team is this. So systems evaluates the risk, cost, feasibility, trade-offs associated with the design. We define internal requirements. We ensure that we are complying with our external requirements. So external requirements could meet something like spaceflight. Spaceflight is our launch provider. Finch has to satisfy a very unique set of requirements to be allowed on board a SpaceX rocket. We coordinate design work between different systems, validate our design work through testing plans, and the role of systems is to guide the team from concept to point, effectively in a nutshell. That is my role, but it's not the entire responsibility of this endeavor does not fall on me. What you'll find is that everyone, no matter what level of scope you're working at across the team, you will be employing systems engineering principles throughout your work. That comes with doing proper engineering work. Okay, so what's a system? Effectively, you can think of it as a combination of elements that function together to produce whatever capability is necessary or to meet a need. Now, a system can take the form of hardware, software, equipment, facilities, personnel, processes, procedures. I want you to take away from this presentation that systems are fractal in nature. I have a very famous fractal here in the picture. Anyone know the name of this famous fractal? The Sierpinski triangle. That's right. Yes. The what? Leaves are a form of fractals, I guess. Yes. Yeah. Oh, you just wanted to add that in there? That is true. They are very famous, probably more famous than this triangle. Anyway, yes. Systems are like this triangle. While they may not be self-similar, which is the property you see here, where regardless of how far you zoom into a fractal, you will see repeating structures. A system may not be repeating in that sense, but it does conform to the fact that there are very strict rules that systems follow at the interfaces of each element in the system. And it's through the compliance to those rules that you end up building a very complex system, that you're able to build up a very complex system that accomplishes some tasks. In this case, it's an imaging satellite. So Finch is very much like a fractal. You think of the system as a whole being the Finch satellite, but it itself is composed of things like the payload, the microcontrollers, the MCUs, the solar panels. The software is itself, although not a physical thing, it is an artifact of the system. It is a system in and of itself. And it's through systems engineering that we direct the growth of this fractal as it evolves. So again, just to support my claim here that Finch is a system, this is a system block diagram. It's an artifact that you'll come across very often in your engineering design work. Every cell, every block in this diagram is a system or a subsystem of the satellite. And you can see that, might be a little bit blurry, but you see that they're sort of structured as almost like Russian nesting dolls. There are systems within systems within systems. And it's through these interactions between the systems. So in this case, these lines depict some sort of information flow between components of the system. So there could be power, data, mechanical, thermal, environmental, doesn't matter. But they're arranged in very intentional ways. And it's through that intent that you arrange a system that works to some goal. So again, it matters the way that you stack like the Lego bricks. That's the takeaway here. If you're curious to see more about the system architecture, we are beginning to migrate to documenting that architecture within this system architecture database in Notion, which will eventually contain entries for all those blocks in the diagram in this format here. Cool. Okay, so let's talk a little bit about the engineering design process. We'll talk about best practices from NASA gods themselves, current practices, and what I intend to be the future vision for systems moving forward. This is our Bible. This is the NASA Systems Engineering Handbook. It effectively describes best practices in the space industry for all systems engineering work. A lot of our process is based on this book. And the reason we follow such rigorous guidelines in the way that we structure our workflow is that that's simply what it takes to go to space. And over the course of the presentation, I'll show you exactly how we are adopting the methodologies and practices that are contained within this book. The one that we're following right now is the Systems Engineering Handbook for revision 2015 or something. It's the newest one, I believe, 2017 or 2015. Okay, so this is the first artifact coming out of the SE handbook. This is the classical engineering design process. This is a very typical image to see in your design courses. It is also called the V model, the system V model. The way you read this is from left to right. So you begin a project or an engineering project using a concept of operations. This is an artifact you develop very early on to effectively define what it is that you want the system to do. So in our case, we passed the stage already. And our concept of operations was we want to build a satellite. The satellite needs to do some science. And this is roughly how it'll accomplish that feat. Then you move on to requirements and architecture. This is like your high-level design phase. So once you know what you want to do with the system, then you have to start defining the specifics of how you're going to build that implementation. Then you move down to detail design. This is actually the phase that we're currently in now. This is the stage in phase that we're in currently, which arguably, in my opinion, is the most fun stage of all, because this is really where you actually get to do the implementation. So at this point, a lot of our requirements and the general system architecture for the satellite has been defined, as you saw earlier. Now is the time where we actually get to start prototyping and building code and building hardware to satisfy those requirements. And then there comes a point in every project where you will invert your direction back up the stack towards your final integration. So everything up until now has been decomposing, solving subproblems into subproblems into subproblems. After implementation, so once that's all done, you then have to integrate everything back together, so start weaving the systems back up to build the system. And as part of that is the AIT process. That's assembly, integration, and testing. Verification and validation fit in there as well. And then, of course, near the tail end of the project is operation and maintenance. So this is actually us executing the system, shipping it off to space, and doing the science that we set out to do initially from the start, through ground control operations or whatever else. My only gripe with this model, and this is something I've had for a couple of years now, is that it doesn't emphasize the amount of cycling that actually takes place over the course of engineering. Hardly is any project as streamlined as this. There will always be moments where you have to go back to a high-level requirement and change it because the system just simply cannot be satisfied according to the limitations we have as a team. Which is why moving forward, I'll be integrating this model for Finch. This is taking a page out of Agile for project management. Who's familiar with Agile? Just show of hands. Okay, not a lot. Fair enough. It's funny because Agile isn't actually taught very often in undergrad engineering design courses, but there is generally two schools of thought as to how to develop an engineering product. You either waterfall it or you agile it. Waterfall is kind of like what that V model is built upon, is the waterfall model, where you set out by describing a set of very high level requirements. You design to those requirements, you develop, you test, you deploy, and you operate. Nowhere in that linear cycle, or rather it's not a cycle, nowhere in that linear path is there an emphasis on iteration and prototyping. This is what Agile tends to solve, or attempts to solve, it is a better framework to emphasize the fact that you have cycles, you have iterations. The tighter you can make these iteration loops, the better the final system is going to be, because it means that you have been testing more and more often. One of the things that we learned over the course of attending SmallSat is a very popular conference that we went to. A key takeaway from that visit, where we got to meet other design teams, is that you cannot emphasize enough the importance of testing, and testing early, especially testing all of your components early, even if they're off the shelf and you expect them to meet the spec. It's very often the case that they don't work as you expect, and so testing even the components you buy from a different manufacturer vendor is important. And so this is what I hope to bring to the team through this transition to Agile. Now, we aren't implementing the full implementation of Agile. Agile tends to be a very software-focused project management framework. There are aspects of Agile that I don't agree with and that I will not be bringing to Finch, but I will show you the hybrid solution that we're going to be adopting. Is this. This is, again, we still follow the same V model for how we structure our development on the design team. However, we emphasize the fact that there are now iterations within each of the stages of this V model. And it's not very well shown here because I couldn't get the diagram quite right, but these loops might stretch different phases. You might have a loop that stretches between detailed design and architecture, or architecture and concept operations. Anyway, the point is, the lines aren't as, they're more blurry than you think. And this is what this iteration approach is intending to showcase or to emphasize. Okay, so let's now talk about the project lifecycle. Just give you an overview of where we are in the mission. We are currently in phase C, this one here, like I said, the detailed design phase. Again, this is where we start implementing, prototyping, building things. To the left of this red line is roughly where we've been, and then to the right is where we're going. There has been several design reviews formal design reviews conducted thus far. Those are the PDRAs, Bs, and Cs. So we passed all these of course of the last 2 years. PDR stands for preliminary design reviews. So those are the stages in the design where the team comes together and evaluates our high-level design as a team. So we give feedback. And there is very specific entry and exit criteria between the phases that define when a mission can move on to the next phase. And those are defined by the NASA Systems Engineering Handbook. That's all documented there very nicely. Yeah, that's all I wanted to say about that. Any questions on the timeline? Anyone curious what this blue thing is up here? What's the blue thing? Glad you asked, Rosie. That is the beginning of our third satellite mission. The way that we structure timelines, it might seem funny at first that we're, right in the thick of building out Finch, but we're also considering starting designing our next satellite. The reason we do that is because we, as a student design team, face a very difficult challenge of knowledge retention. Every year, of course, we lose members, they graduate, they move on. And it's typically the senior members of the team that have accrued the most knowledge over the course of their time on the team. And so what we hope to accomplish by condensing the timeline between or overlapping the several missions together is to have the members who have accrued the knowledge thus far to contribute actively to the beginning of the next mission, so that knowledge that they've accrued on this one can be applied to the next, so that people aren't starting from scratch effectively at the next phase. It's sort of kind of what we're doing or have done now with Heron and Finch. That's why we have 2 ongoing missions. Heron is currently, close to end of life, or close to launch. And yet we are, again, also pursuing Finch at the same time. So same deal is going to happen again in the near future. Anyway, just in case you were curious. Right, so this is what the actual official NASA definition for what phase C entails. To complete the detailed design of the system and its associated subsystems, including its operation systems, fabricates hardware, code software, generate final designs for each system, and of course, structure the end product. Cool. Okay, let me take you through the systems engineering engine now. That is that model I showed you a second ago, this Agile model. And we'll take it through step by step. So we'll start off with requirements. We have a database in Notion that we're migrating to house all of our requirements. This is going to be our single source of truth for all requirements moving forward relevant to the Finch mission at all levels. So the nice thing about Notion's databases is that they enable you to have relational properties that relate to other entries in that same database. And so you can build up trees, very nice trees in this way. And I'll talk a little bit more about the specifics of requirements, but it's suffice to know for now that they are hierarchical in nature. So you have parent requirements with children, those children have children, and those children requirements with themselves have grandchildren. And so this is what we hope to better portray or house via this new framework and Notion that we're migrating towards. Currently, all of them are stacked up in one Google Sheets, which is very ugly too, very hard to traverse. So this should be much nicer to work with moving forward. Okay. Right, I'll talk about this now actually. So what's a requirement? A requirement is a description of the system under design. They tend to be classified into functional, performance, environmental, programmatic, but the label doesn't really matter. The important piece is what they really mean. The last bullet point there makes use of qualifier keywords such as shall and should to specify the degree towards which requirements must be met. You might have already come across some requirements in your engineering classes. There are effectively 2 types. There's shall and should requirements. Can anyone guess what the difference is between the 2? Matthew.
Shall is like there's less chance that a higher chance.
You got them flipped. So shall requirements are requirements that must be met by the system under design. Should are requirements that are best implemented by the design, but they are not required to achieve the acceptance criteria of the system. And to your point there about chance, these aren't predictors. This isn't something that we leave to chance. This is something that we take ownership of and that we design for. So when we say shall, we are saying, yes, absolutely, we will satisfy this requirement over the course of our design. When we say should, we say, we might slip up on it, but we'll try our best to achieve that requirement. That's really the distinction is between shall and should. There are other conventions for requirement naming, such as RC 1102 or something, that have more steps in the distinction between shall and should. There's like a shall, should, may not, cannot. But really, at the end of the day, these are the 2 that NASA uses, so we stick to these. Okay. Anyway, on a more artistic thought, I want you to think of requirements as being sort of like, this might be a bit of a stretch, but sort of like an artist's brushstrokes. You paint a system from the ground up by writing requirements. This is the magic of requirements writing. And it's the reason why, to me, systems is so fun, because you are in effect defining what the final system will look like without the implementation of it. It is effectively a painting, a projection of what the final thing will look like. And you use requirements to model that in a sense, before it's actually a real physical thing. Anyway, so that's why requirements should be cool. You should care about them a lot. All right, here's an example of a requirement. This was very nicely donated to me by Maggie's team. This is a payload requirement. Maggie, do you mind reading that off for me? Is it blurry? Okay. Yes, if you don't mind.
I think we're still using the same but it's a structural performance numbers when you generate the requirements that literally went. So it's a functional the system is corresponding to the payload. Qualifiers shall once so the description of the payload shall not change the mark safety 50% under quasi-static modes for 70.5 all axes. So this was derived from the NASA guess. Guess this would be accepted for all. So basically, we have different requirements for the structural loads. One comes from the actual launch providers, spaceflight, but because a lot of our members have to send in the just use like broad numbers that have accuracy. Anyway, so the rationale is it's gained by calculating by
No, that's good. Thank you. Just want to get the point across if this is a legit requirement. There's a couple key things I want to mention here is, like I said, every requirement has a parent. Well, not every requirement, the parent, the origin requirement for all of this may not have a parent itself, but for the most part, requirements will have parents. For the most part, they'll have children. That's what these properties capture. You have the type of the requirement. Anyone know why we put a rationale for a requirement? Matthew.
It's the reason why.
Yes, so that is what a rationale is. But yeah, the underlying reason though why it's important to have rationales for all requirements is that say that you are the team of the future and you did not get to meet the makers of this requirement. You need to know exactly why a requirement is in place. Like what really does this satisfy? What is the purpose of satisfying this requirement? Otherwise, it's very easy to say, oh, let me just disregard the requirement. If you do not know its origin or its rationale for being included as part of the makeup of the system. Yeah, Rosie. Thank you. Wait, no, isn't there like two spellings, British and American? Oh, that's rational. Yes, thank you. That will be fixed. Cool. There's also two other properties I want to highlight here at the bottom. There is a relation to trades and test plans, and I'll talk more about what these are in a second, but just know that every requirement should be itself traceable to a test plan and a trade. A test plan is a form of documentation that specifies how we plan to confirm that the system has met that requirement. So that's why it's important to have requirements traced to test plans. The trade relationship here comes into play when you consider that as a designer, you will not necessarily know all the values that you have to specify for any particular requirement. There might be some that depend on other requirements. And so in that sense, you can end up with very complicated relationships between requirements in a system. So say, for example, the signal to noise metric of the payload, that's SNR. It itself is related to our choice of slit width for the payload, as well as the choice of the sensor, as well as the choice of the lenses and the elements inside the optical track. There's a lot of things that come into play here. And if we were to try and constrain, it's a project in and of itself to try and constrain the slit width that we want out of the system. And for that, you need trades. You need to run analyses and determine, okay, we have two free variables. Where along that curve of two free variables do we want to land to constrain that? And so in that sense, you might end up a trade. You might end up having to pursue a trade before you can settle on a requirement. And so that's what this tries to capture here. Cool. Okay. Moving on. So we just passed requirements. Let's take a look at what design entails in this agile loop. So mathematical modeling is, of course, one way of conducting design. In fact, it's a very elegant way of conducting design. And we have a database set up in Notion just for that. It effectively captures individual bite-sized equations that model some aspect of the system in these equation cards that you see here. So we have a couple of them that have been documented thus far, and we're continuing to migrate more. As part of mathematical modeling, you might also come across things like trades, which is what I said earlier. So there's a different database for trades. The mathematical modeling almost always feeds into trades, not always. But again, that slit width example that I gave a second ago is one example of a trade that is ongoing. Another one that maybe isn't necessarily so quantitative is our decision between pursuing an all-in-one ADCS module and a commercial official composite. That's a conversation that's happening very prominently right now in systems you might have heard of. Anyway, so those are captured here in the trades. Actually, I was going to invite Kang to present this example of a mathematical modeling report, but he couldn't make it. So ADCS has a very nice document that they've produced that documents the theory, the mathematical basis that goes into creating their ACS toolbox models. So they started off by defining, the mathematical formulas and equations that they would need to run their simulations, whatever else. And then they follow that up with an actual implementation code. So that's sort of where the dynamic is between the design and the development phase in that agile loop. Okay, now we're on test plans. So a test plan is effectively some form of documentation that specifies exactly how you're going to test some aspect of your system. They detail the objectives, the resources, the processes required for testing, and we use them to verify the requirement or even a group of requirements are being met by the system. So the reason actually that development of test plans should generally come before design, or sorry, this is build. Anyone want to take a gander, a guess as to why you might want to develop a test for a system before you implement the system? Yeah. Well, you wouldn't know it unless you tested it first. So I'm asking, why do you develop the test plan before you actually build the thing, the implementation? Okay. Oh, you just missed your slide.
What?
Yes. Never mind. All good. Yeah. Exactly. That's exactly why. It's generally considered good practice to develop your test plans before your builds so that you don't introduce biases that could make it creep into your test plan such that you bias the test towards passing, given your final implementation of the thing. This is a very common trope in software engineering, where you always want to write your tests for software before you write the software thing itself. This is part of what's called test-driven development, and it's what I plan to bring to the team in the next few months. Is that logic? Okay, I'll hand it off to Oren to talk a little bit quickly about the TVAC testing plan.
All right, so this is the Finch thermal vacuum testing plan, which is something that me and the rest of Thermal have been putting together for the past summer. Like David mentioned, we make our testing plans like far before we do our testing. So TVAC is actually supposed to happen close to the launch, so in about a year and a half or 2 years, but we still have the plan like sort of done. So that goes to show like how we plan to get rid of bias. So TVAC itself, it's basically it's a way of making sure that all the subsystems integrate seamlessly with each other and they work in the conditions of space. So what TVAC is thermal vacuum. You take all of Finch integrated, plug it into a big metal box, pressurize it down to the vacuum of space, and then you use heating and cooling devices to simulate your orbit. And by doing that, you can simulate the conditions of space, and you can see things such as, is Finch maintaining their nominal temperatures? You can confirm its structural integrity, and you can establish the ability to image. And it's really important you do that in a systems level basis, because you can imagine that if you do things like, for example, Finch might be good at imaging when it's just the camera, but when you implement all the circuitry and all the thermal stuff and put it into the actual bus that it's going to go up in, it might not image just as perfectly as you'd expect it to see. So it's really important that once we integrate everything, we test it, but we also test it before we integrate everything. And this is just, click. Oh, nice. All right, this is just a really quick overview of a thermal vacuum test procedure. It's one of the images in the procedure itself, which actually details everything that we're going to do during this. Right now, it's about 2 days long, our test procedure, and it details every single minute what's supposed to happen. So you can see some of the biggest takeaways from this thing is that you can see that we're cycling through temperatures. So trying to see, hey, can a structure withstand this sort of thermal deformation? Can the camera stay in its optimal temperature range and all this stuff? And you can also see there's some little colorful dots, and that's testing functional testing. Can we take a picture when it's cold? Can we take a picture when it's hot? Can we take a picture when we're moving from hot to cold? And that's just the picture stuff. We can check data handling, we could check processing, and all this sort of thing. So really, a systems level TVAC document is exactly that. We're putting the whole system together and seeing if it can do what we want it to do.
Cool, very nice document. I suggest people take a read if they're interested in that plan. Okay, so moving on then. So once you've developed the test plan, you are then in the realm of builds. Builds can be either physical or non-physical. They may take the form of software, hardware, anything in between. And they are generally scoped to varying levels of fidelity. So for example, there's one build here that I'll talk about in a second. This is the Finch Eye Cyber. This is a prototype build of our optical payload that is being built digitally in an optical simulation engine. Contrast that now to our physical build, Finch Eye Embryo of the payload, which I'll talk about now. This has been developed by the optics team for the last couple of months now. It is the first prototype build of the Finch Eye payload. And it was designed with accessibility in mind. So every component you see there, the selection of those components, they are available off the shelf. And so a lot of the work was done into determining which components are the right ones to enable us to have a platform for future development and iteration on the payload design. And so that's what this is. And so this is an example of a very, very hardware physical build. But of course, there is alternatively a digital version of this, which would also be considered a build. And we're in the process now of fleshing out the test plans to test this build. If you're curious about the component list, here it is. You'll notice that there's a lot more here than you'd expect. That's because a lot of the components, the majority of the components actually are OptoMech. So they're the housing, the standoffs that you need to actually put everything together in 3D space, as opposed to the actual optical components that you care about, which are just these 1, 2, 3, 4, 5, 6. It's an expensive piece of hardware. I think it came out to Maggie, do you remember the final number? Finch Eye? Yeah, it's like 3,000, 3K. Yeah, including the OptoMech. Nothing compared to the cost of a camera, of course. That's more like 20K. Okay. Nice. So let's say we finish the build. The next stage in this feedback loop is, of course, the feedback. It's the design reviews. These are the formal opportunities that we have as a team to present our work to each other. They generally span cross teams, but they can be intra-team design reviews. Maggie will give you an example of what these look like in a second. They are opportunities for the team to present major milestones. We assert the critical exit criteria for the phases that are being met. And of course, we receive feedback from the team. So we are migrating all of those recordings will hopefully soon be in Notion or accessible through Notion for our historical design reviews. Maggie, yeah, you want to talk a little bit about what those entail?
Here. Okay, so hi everyone. I'm Maggie. I'm the payload mechanical design lead. So yeah, just giving an example of, a design review that we had this summer. So it's not quite a PDR, it's not quite a CDR, but it sort of marks the milestone of us entering detailed design and, doing a little bit of work. So there's a couple things that it covers, but a high level, overview of it. It's a review of all the work we're doing, and we'll have we'll usually carve out like a couple hours that day and sit down and go through a long presentation and invite some advisors to give us feedback, and hopefully everyone on the team also gets a check-in. So the things that we sort of document in these are like the detailed design decisions, or for this one, yeah, detailed design decisions and major trade-offs that we might be doing. So an example would have been the optics component selection, payload mounting or the prism housing. Some verification and validation pipelines. So after we've, initially done the testing plan, as David mentioned, as we go through the design, a lot of that will change. So, just updating everyone on how we're doing with those and if there are any new developments. So for example, the STOP, which is the structural thermal optical performance analysis, and how we'll be carrying that out, as well as prototyping, which is pretty important in the detailed design stage. And so we'll also introduce things like preliminary testing results, or at least we did during this design review. So that was something that we also did in simulation to validate our design, and prototyping would be for verification. So additionally, we'll have things like risk mitigation and descoping. So as we go along in design and we find, new things, how are we going to deal with this? So optics handling guide is an example, as well as the ground truth validation contingency for scientific mission. And of course, we also talk about some upcoming milestones and deliverables. So it's really just a check-in with everyone.
Okay, so that brings us to the end of that whirlwind tour. Again, to summarize, this is the framework that we'll be continuing to implement over the next few months as part of our endeavor to improve our systems practices on the team. Okay, enough of that. Let's talk a little bit about, sorry, Rose, I just saw your ping in random. Let's talk about project management and how we handle that aspect of things on the team, because that does fall under the purview of systems. So we are again taking a little page out of the way that Agile structures projects. Generally speaking, we categorize all activities on the team into three broad areas. Those are epics, stories, and chapters. Epics are effectively large system spanning initiatives. They are things like detailed design, concept of operations, high level design. Those are the big chunky sections inside of the V model you saw earlier. Stories are smaller than epics. They are time-bounded pushes to complete a set of related tasks within that epic. And then chapters are themselves a smaller unit of stories. Of course, chapters make stories, stories make up epics, and epics drive the mission forward. So I'll give you a concrete example of what this all means. So take, for example, the detailed design epic. That is an epic. A story within the detailed design epic might be the ADCS all-in-one versus commercial off-the-shelf composite decision that Kang's team is working on right now. And a specific chapter within that story might be the investigation into alternative all-in-one ADCS modules. So that's sort of the breakdown of the way that we structure our tasks on the team. Here's actually an example of one. Actually, this is a chapter page. Yeah, this is design 3D printed mount for, it's got off there, the Fleur towel. So this is a chapter. This is a real chapter that one of our members is speaking on right now. Another thing that I want to highlight here is the fact that all chapters have either an assignee or a reviewer. So the assignee would be the person who's actually undertaking that chapter, that challenge. The reviewer is responsible for defining the task. They are generally going to be a lead or a project lead. They track progress, they give feedback, and then major feedback once a chapter enters the review stage. One thing that I want to emphasize, and this is the same way that Agile structures their project management on for things like software design, is that the reviewer has the sole power to move a chapter to complete once it's confirmed that all intended goals have been met. The rationale behind structuring our work this way is that we want to avoid situations where a chapter has been moved from review to complete without a review stage or without actually having met all the intended, the intended purpose of that chapter. So we instead have a reviewer whose goal it is, or whose job it is, to move that from in review to complete once they're satisfied with the outcome of that chapter. Okay, so that's that. If you're ever curious as to where all your projects are ending up, if your leads are abiding by this framework, my dashboard is a great page to check. This is in the homepage, I think, of the Notion workspace. Is effectively your personal ground control. You can go here and check out all your assigned projects for the team that you're taking on right now. If you're a lead, you can check out the for review section of that table, and you'll see a filter view of all the things that you've been assigned to as a reviewer. So if you're a lead with a lot of members, it's a very nice way to, at a glance, see everything that's happening all at once and check in with members over the course of development. So that is project management in a nutshell and how we run PM on the team. I'll give you an overview now of the productivity ecosystem. So the ecosystem is the curation of tools, platforms that we use on the team for any sort of development work we do. You'll have already been introduced to many of these, but if you're curious to see all of them, so this is the complete list, save for a couple of things that haven't been reported yet. You can check out the tools and platforms database, which also exists in the workspace. It's of course a database of all the tools and platforms that we use on the team. Here you will find onboarding instructions for most of them. If you're a new member, you need to get started with the tool that a lead recommends you. Be sure to check this out. They might also point you to it directly. And there's other, meta stuff here for IT in terms of setup for a server, that kind of thing. At a glance, though, this is roughly how our ecosystem is laid out here. Everything is traceable, as you can see, to Notion. That is our hub. That is where all our activities take place. Of course, we use Slack for communication. We upload our recordings to YouTube. The reason there is because the Zoom Cloud actually deletes your content if it's been there for over a year or something new they introduced a couple of months ago. So we have to move those over to YouTube or keep them on the drive for mass storage. That's the group drive. You might see some artifacts existing within Overleaf. That's a LaTeX writing engine. Very nice platform to use for writing academic documents. Of course, Google Sheets for basic computation and GitHub for advanced computation and source control of code. CAD is also in there, but really it shouldn't be. We're working towards getting a dedicated CAD server from IT so we can move our CAD to a better place than GitHub for that kind of thing. Our team roster is on Notion. Meeting minutes are on Notion for the most part. There are, of course, differences in the lead and the way that leads will run their teams, but for the most part, this is the de facto standard. A page I want to highlight inside of the workspace is the Zen of Engineering. This is a page that captures a lot of the operational and design principles that we have adopted on the team. They're effectively learnings that we've come across over the course of our design and iteration. It's good reference in case you ever have to make a decision that isn't just based on the numbers alone, especially for things like trade-offs. So I'll give you a couple examples here. Simple is better than complex. Complex is better than complicated. Beautiful is better than ugly. Explicit is better than implicit. And these are more or less based on the Zen of Python, which maybe Python gurus might have come across in the past. So that's that. That's the Zen of Engineering. We have another database where we curate papers and resources of all kinds, including our own literature, the stuff that the Utah team has produced, like academic writing to, on informal, like formal papers, that kind of thing. Those are all stored in the Library of Babel. Teams will generally have a bookshelf, which is a view of this huge database on their team homepages. And we tend to use those to store things like papers that we read and we come across that relevant to the design work on those teams. They will generally end up in the Library of Babel eventually. Meeting notes, like I said, nothing new here. These are all accessible via one database. And of course, teams will again have views of this database within their team homepages for their specific team's meeting notes. Storage is another one that people might not know about. We have a digital registry going for physical components we own and have in the lab. So things like our floor tile will be uploaded here at some point. This is a nice way of cataloging all of our physical hardware that we know that we own in the lab, so that down the line, if the people that bought those items initially leave, people will know what exists in the lab and where it's been, where it's stored for easy traceability. Oh, okay, I'll move faster. We're almost done. Okay, so the design challenge. I'm gonna give you a prompt. Here's the design challenge for today. It is a remote sensing for mineral exploration challenge. And here's the prompt. You are a team of engineers, very skilled engineers, working for the Wakandan Technological Institute for Aerospace Service, that's WTIS. Your team is presented with a request for proposal from a vibranium mining company. They wish to build a remote sensing satellite that can detect the location of surface deposits of vibranium over Africa. So your task is to devise as many requirements as you can for the satellite within the time limits. Okay. Before we start, I'll get you guys to join the Slido. That's how you submit your answers. And I'll pull it up here. Let me set up a Slido on your end, Rosie. You'll go to that website, slido.com. Wait, Rosie. You don't have a Slido for it. I'll just put it on. Oh, that's not gonna work either, is it? Because you're recording on this one. Oh, why don't I just share my screen on Zoom? So that'll stop yours. Perfect. Okay. You log in quick. Nice. All right. Starting in 5 seconds, you'll have 1 minute to come up with as many requirements as you can. Say again? It's that one. Oh, the prompt. Yes. Yeah, let me flip back. There you go. Okay, time starts now. And if you want an example, that's your example. You need a description, at least. The poll disappeared. Oh, shoot. Did you guys lose your progress? Oh, my bad. Okay, I'll leave it there. So again, the anatomy for requirement, you must have a qualifier, you must have a description, and you must have a rationale. Those are the 3 things we're looking for. They can be as fictional as you want to, but we need to see that structure for it to be a valid requirement. "30 seconds left." Oh, they're coming in now. "10 seconds." 5, 4, 3, 2, 1. All right, time's up. Nice. Let's read what we got. Shall be able to gather data on the mineral content of the ground surveyed. Shall be able to detect the quantity of vibranium. Shall be able to, where to go? Shall be able to sustain orbit above the ground. Nice. Qualifier. Ooh, no rationale though. Couldn't help but notice that one's gone. Yep. Qualifier during operation, question mark. Description, shall operate in under the conditions of space. Rationale, the primary purpose of the satellite is to detect vibranium possible from space. Therefore, it must be able to function in space. Good. Description, shall be able to detect and locate vibrant deposits with reasonable precision from something. Rationale, basic function. I think that's a basic function. Shall be able to withstand vibranium explosions. Good one. Wait, from space. Justification survive. Good. The orbit of the satellite needs to be SSO if the camera requires sunlight to operate. Not necessarily. Our satellite is in SSO. Or sorry, it is. I thought you said, sorry, I thought this was geocentric, geostationary. Good. Shall be able to maintain temperature of the vibranium camera under 4 degrees Celsius, or in Y.
Vibranium can't be detected above 4 degrees.
Good, good, very true. Must have a detecting system. The satellite can be at the right location, can tell where satellite is, can communicate data back. I think these are 4 separate ones. The structure shall be able to handle 350 Kelvin at all times. This is so it can handle the radiation coming from space. The structure should be able to, shall detect vibranium. If it doesn't detect vibranium, it is useless. And it's also a very good requirement, yep. Shall be able to image within spectral resolution required to resolve vibranium absorption features. Nice, very thorough. There shall be a permit from the countries. Oh, I like this one. Whose aerospace we made so we don't get in trouble. Who wrote this one? Nice. We could use you for Utah legal. Okay, test. Nice. Okay, thanks for playing, guys. Those are great. You got it. Like, this is more or less, the kind of work that we do to come up with requirements. Of course, they're not so fictional, and they're usually derived from actual real sources. But this is the gist of how we conduct requirements writing at its core. Example, and that's it. That's the end of the crash course on systems engineering. Hope you guys learned something today. So I know we ran a little bit over, but if anyone has any questions in the next 60 seconds, feel free to ask. Yes. I'll hold off for questions. Say again. I can speed run questions right now. Try me. Yeah.
When we were making requirements, how do we have to come up with requirements? Do we just throw stuff at the wall, or are there certain things we look for in requirements?
2 things. One is there are some very high level requirements, as in from launch, that need to be met. And so those requirements, it's easier to work with them because they effectively just trickle down the system. So in the case of Maggie's payload, we have a very specific vibration testing that we have to be able to pass, right? Launch on being on a rocket, you can't have the satellite breaking apart in front of you. So those are not always easy, but what you need to design for. It's vibration. Okay, so we have design for vibration. How much vibration? Okay, we have this number from launch. Let's test to that. And we'll write a requirement says the payload must be able to satisfy this vibrational profile. There are others, however, so in the case of, I'm speaking a lot to payload because that's where I have done a lot of my work historically, but for payload optics, there are requirements that we have to arrive at through research, as in either looking at reference designs for other optical payloads that exist, first principles, so knowing what really is a hyperspectral imager, and from that gauging if we want to satisfy the scientific requirements, what does our system need to be able to do to arrive at those requirements, or to arrive at satisfying those requirements. At the end of the day, it's part it's part knowledge curation. So like learning things about the thing that you're engineering, a little bit of creativity, and being at the whims of, you know, the parent requirements. That's really what it is. Yeah. Yep, that's a great open question. Yeah, so like what Rosie said, historically, there are times when, so the dynamic we have on the team, and this is something I bring up in the presentation, but I can do it now, is we have a science team who is like our primary stakeholder. They are the client. We are designing the system for them so that they can conduct their science work. Of course, they aren't really a client. And so we have some leeway in terms of what we can push back on in terms of the requirements that we're capable of satisfying. So if there's a requirement that science says, hey, we need a 1 meter spatial resolution out of the system, we can push back and say, yeah, no, we can't, because we simply don't have the expertise nor the resources to accomplish that in our system. And so that is where you get into this loop of, you know, saying, okay, science needs 1 meter, we can't do that. Do you want 5 meters? And they're like, not really, but okay. And there's other times where science simply doesn't know what requirements they need to impose on us. And so it's up to us then to do our due diligence and say, okay, well, this is, you know, from reference designs, from rough back the envelope calculations, this is what we think we can achieve. And then science will scope a mission to abide by those requirements, that will be satisfied by those requirements. How you resolve that feedback loop where you say, yeah, we can't do this. Oh, wait, can you do this? I have some thoughts, but I will share them later. I can't think on the spot. There's also a law. Yes. Yep, you can't let them be in orbit forever. There's also, so I think someone already brought this up, there's very strict imaging laws. You have to get approval from the government if your system is like has very high spatial resolution. It can be considered like a spy satellite. So you have to be very careful about the process you follow to get you know, permission to image at that resolution from the government of whichever country it is that you're imaging. But yeah, any other questions? Nice. Okay, that's a wrap. Thanks for coming, guys. If you're online, see you later. Thanks, guys.